welcome you all for the PhD Defense Viva of Mr. Suraj Bhoyar, and I welcome our external for this particular PDC external experts, Dr. Subhash Deshmukh to MIT ADT University, the internal for the PDC, Dr. Sachin Pawar, Supervisor Virendra Bhojwani sir, and the members, Kishore Ravande sir is here, Atul Patil sir is here. I welcome all for this PDC Viva, and we can start with the presentation. After the presentation of Mr. Suraj Bhoyar, then the Viva, it will be open for the question answer sessions. And so then I request Mr. Suraj Bhoyar to start with his presentation. And all, it is hybrid also, na? Kitna Suraj, sir, you may present your work in 40 to 45 minutes max. And I also welcome the online members who are present here for this particular Viva.
Hello, 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 hello. Very good morning to one and all. Thank you so much for gracing this occasion. So let me welcome you for my PhD Open Defense Viva Voce. So before I begin, let me start with the Gurur Brahma, Gurur Vishnu, Gurur Dev Maheshwara, Gurur Sakshat Parabrahma Tasmai Sri Guruve Namaha. So, Namaskar, I am Suraj Bhoyar, and today I will be defending my thesis entitled Parametric Investigation of Special Purpose Flexure Spring Used in Cryocooler. And I am so much thankful to Sri Dr. Deshmukh sir, Dr. Virendra Bhojwani sir, Dr. Sudarshan Sanap sir, Dr. Sachin Pawar sir, Dr. Priya Singh ma'am, Chairman PDC, Dr. Kishore Ravande sir, and all my dear colleagues. Thank you so much for joining. So let me set the context very quickly. So my dear friends, what would happen if all the satellites stop working and if people on Earth were not connected? Can you imagine a world without satellite? We don't always realize how much we depend on satellites orbiting our planet. So what would happen if all stopped working? What about GPS? What about internet? 3G, 4G, 5G, 6G, 7G, even smartwatch or telecommunication. So GPS satellites are little more than highly accurate atomic clocks in space which transmits a time signal back to the Earth. And without satellite imaging, we would not have access to the vast amount of information and insights which we currently have about our planet and the universe beyond. Like for weather forecasting, satellite imaging provides us crucial information about weather patterns, allowing meteorologists to make accurate predictions about the weather. Even for agricultural, we used to monitor crops, soil conditions, providing farmers with the data that helps them to make informed decisions about cultivation and cropping, even irrigation and fertilizers. Even for disaster response, like the recent case happened in Turkey. During like hurricanes or even wildfires or even natural disasters, definitely we could get the real-time information to the extent damage happened and everything. Even for defense and security, surveillance, for military operations, or even for environmental monitoring, which provides valuable data on the health of our planet's ecosystem, right? So without satellite imaging, it would be much harder to gather this kind of data. And my dear friends, cryocoolers are very much significant for satellite imaging and particularly for IR sensors in camera because they are used to cool the sensors and other components in the camera to very low temperatures. And this cooling is very much necessary because IR sensor detect and measure the heat emitted by the objects, and this amount of thermal radiation emitted by an object decreases as the temperature decreases. Therefore, cryocoolers are devices that produces and maintain these low temperatures. And they work by removing heat from the sensor and maintain typically minus 200 degrees Celsius. So they work by removing heat from the sensor and other components. And cryocoolers are the critical components which helps us to reduce the noise in the images. So to increase signal to noise ratio, to improve the resolution and quality, to improve the objects captured IR spectrum with greater accuracy, cryocoolers are very much critical, right? So as you can see from space station, beautiful images and other, all these things are possible with the help of cryocoolers. So what is cryocooler and why do we consider Stirling cryocooler which uses free piston and free displacer to achieve this cooling? So the process starts with the piston. Yeah, the process starts with the piston compression working at mostly helium most of the time, which is located outside the cold space, and this compression of gas generates heat which is then transferred to regenerator. Okay, then regenerator acts as a heat exchanger which transfers heat from compressed gas to the working into the cold space. This results working in the cold space becoming hotter than the gas in compression space. Then free displacer moves downward, pushing the working gas in cold space towards the compression, and as the gas moves, it expands and cools, absorbing heat from the generator. So the cold gas in the cold space flows through the generator, which again get transferred to the heat absorbed during the absorption process and expansion. And the upward movement of displacer, this free displacer then moves upward, drawing the working gas back, okay, which again the same cycle goes on continuing with the piston compressing the expanding the gas and the free displacer moving. So this is the actual fatigue life setup which I will be also demonstrating today. So it creates cooling effect. And the most critical component in cryocooler which provides compliant mechanism for linear motion is nothing but the flexure spring. So this is the most critical component. And what it does, it keeps the piston in desired motion and position with a specified level of stiffness. Like I do have flexure spring, so desired stiffness it provides. Then it also allows free piston to oscillate in the freely in the axial direction. It also provides radial stiffness. The most versatile or best thing about this flexure spring is it acts as a spring in axial direction and it acts as bearing in radial direction. So it provides radial stiffness to prevent the free piston from touching and rubbing the seals, which maintains tight clearance. It also helps to dampen the vibrations. Okay. Also, flexure spring helps us to extend lifespan of the cryocooler, because in space where we are talking about cryogenic temperatures, lubrications are not possible. So in that case, how to have maintenance-free mechanical moving parts? So overall, flexure spring enables high-frequency operations and low thermal conductivity, resulting in more efficient and reliable cryocooler design. So moving on, why to go for free piston, free displacer Stirling cryocooler? So the most important is high efficiency, because these cryocoolers have high efficiency compared to other types of cryocoolers, which means it can achieve very low temperature using less power than other cryocoolers. It also comes with the compact size. The video we have just seen. It is very compact cryocooler which makes ideal application for where space is limited. And it can be also integrated with the other systems where we do apply it. Low vibrations, which is again very much necessary. As I talked about satellite imaging, vibration has to be low. So it produces very low levels of vibration, making it suitable where vibrations can cause problems. High reliability, since due to its simple design and few moving parts, it operates for longer period without requiring as such maintenance. And the most important thing is no radial forces, just like rotary compressors. There won't be any radial forces. So instead of that, this will have only free piston which moves back and forth, right? And again, it don't have any walls because mostly the walls relies on the movement of the. So this simplifies the overall design. Now let's talk about quickly about the challenges for space application. Like for space application, these are the requirements, right? Low temperature, low energy consumption, less weight, limited space, stability for satellite imaging. Mission life shall be greater than 5 to 10 years, because when we launch satellites, definitely we do expect based on, if it is small satellite of 10 to 100 kg, mission life could be 5 years, but if it be large commercial, 10 years. No lubrication, maintenance free service. Now how this, because see in space application, like satellite imaging, telescopes, low vibrations helps to improve the accuracy and image quality, like we have seen. So to get those, vibration basically causes distortion in images and even noise. So low vibration is the requirement. So we do have the solution. High efficiency, compact size, and this is free piston, free displacer. So the ultimate aim is what? We shall have fatigue life of flexure spring, which we considered as a critical component for cryocooler, shall be greater than the operational life of satellite or cryocooler, and it shall be also greater than the mission life of the satellite. So rather than this, there are again multiple applications. Sorry. Yeah. So rather than this application, there are again multiple like earth sciences, even astronomy, security. So cryocoolers have different applications. I'll skip this. So why is flexure spring? Why do we consider flexure spring? Because success or failure of cryocooler majorly depends on flexure spring, because it eliminates wear as well as frictional losses with the vibrations. You can see here, we have just seen flexure mechanism. So as we discussed, it keeps free piston in the desired position. It also allows to move it, oscillate freely in axial direction. Radial stiffness it provides in so that we can have without touching the, and it also helps to dampen the vibration. So the basic advantage about this flexure spring are they are nothing but the thin metallic disc with slots cutting, right, which permits axial motion, as well as it also acts as a bearing in radial direction. And the major advantage is it's very simple, very inexpensive, easy to manufacture, compact, lightweight, right, and easily manufactured using photochemical etching, long life, very much reliable and noiseless. So we are going to explore all this. So as I discussed earlier, it acts as a bearing in radial direction and it acts as a spring in axial direction. Okay. So because most of the other metals also we'll be discussing, they will tend to experience fatigue by repeated flexing and other. But that's how it becomes very much necessary. So quickly, structure of my thesis. Chapter 1 talks about theoretical framework. Chapter 2 talks about literature, where we have taken and also done scientometric analysis. Chapter 3 talks about flexure spring analysis, where we have done some mathematical modeling and we derived some equation. Then finite element analysis, extensive. We have done a lot of iterations. Even based on the iterations and data, I have also made dashboard, where any further researcher would like to continue, he has to just put the parameters and he will get the result. Chapter 5 talks about experimental investigation and validation, where we have developed setups and we have validated. Chapter 6 talks about results and discussion, conclusion and flow. So quickly I'll share you literature and the gaps. So right now, if we talk about cryocoolers, the market is anticipated to increase from 2.51 billion to 4.45 billion by 2030, right? So it has compound year growth of around say 6 to 7%. So, and they have been mostly used for say renewable energy application, micro scale Stirling, then advancement in materials and manufacturing techniques, hybrid cryocoolers. Most of the biotech applications now, even for NMR, MRI, all these cryosurgery and all these things are very much possible using cryocoolers, right? So the use of flexure springs in power system began almost in mid 1980s or early 1990s, you can say. Initially, it was focused on linear compressor for cryogenic purposes. But then Oxford University, they used flexure bearing first time in cryocoolers, and they demonstrated the promise where we can have long life, like for more than 40,000, 50,000 hours of operation. So even Mark, he came up with the novel triangular, sort of geometry. Then Mr. Gaunekar, he also created analytical procedure. He created some design charts. Then measures, again, he started first time using this for tactical applications, for defense applications, right? And even modification he has done. Even then, after rollings, he has taken forward. Then extreme temperature ranges, he also tested with various material options. Even Honeywell, Hymatic organization, they also find out the relation. Then Simcoe was the pioneer to identify the crack propagation using SCM and other, how crack gets started because of the repeated flexing and other stuff. Then Peng, he carried out research work to analyze stiffness. Then multiple research, but there is what we can say lack of data where we can have a modular design as well as design charts. So even we have done scientometric approach. It has revealed several key trends about this particular topic moving forward. So even this analysis, you can see it shows citation-based literature mapping and timeline. Okay, so how it is very much correlated. Even you can see papers published by us, so it has correlation. We have used multiple tools. Even you can see number of publication year-wise by the time cryo coolers started using flexure springs. Even we have done tree map where from which publication who are publishing the. So this involves also examining the credibility of the research work going on across the globe. And we have also done analysis country-wise because it gives us cultural, political as well as social context, what sort of research is going on. So topographical also we have done so that collaboration opportunities can be very much possible, right? So this is the scope of work and white space mapping for a special purpose flexure spring, where we have considered, we have break it down to several different tasks like space application, ground application, even for model analysis for space and ground. Then we carried out parametric investigation, how parameters are important, what are their critical role in overall mission life, right? Then even for higher strokes, can we go for it? Then because again, natural frequency, every product has their own natural frequency. So we also evaluated and we have tried to find out where it matches, because so that we could achieve the resonance and we could lower the energy consumption. Then hardware has been developed, even material option also worked out. And then we also use fast Fourier transform to analyze the same. So let's talk about research objective one by one. So first was to develop an FEA model of the spiral arm flexure spring, where we have applied boundary condition, pre-processing, solution, post-processing, and accordingly mesh independence test was also carried out. Then how to find best geometrical configuration, how to arrive on the conclusion that this is going to be best, this is going to have better mission life, right? For space as well as ground application. We have also analyzed stress distribution, axial stiffness, radial stiffness, fatigue life, modal frequencies for parametric iterations. We have also performed model analysis for achieving resonance, as I discussed. To design and develop test rig. So we have developed multiple test rig to validate stiffness, modal frequencies, and most importantly, fatigue life, because fatigue life decides the overall life. To again validate, we have validated analytical and experimental findings, and overall to achieve low operating stresses and infinite fatigue life for spiral arm flexure spring. So once again, I would like to reiterate this. So fatigue life of flexure spring matters a lot, because on this operational life of cryocooler is dependent, and on the same mission life of satellite is dependent. So let's quickly jump on to parametric consideration. So you can see this is an exceptional unit of flexure spring, thin metallic disc. You can see number of spirals, right? And it has been clamped over a periphery. So every unit is like thin metallic disc. So we consider these multiple parameters like geometry of the flexure spring, number of spiral arms, how many number of spiral arms, 2, 3, 4, width of spiral cut. Okay, then angle of rotation, what would be the sweep angle, that is angle between the axis of rotation and the tangent drawn to the curvature of the spiral. Then modification, because definitely when we deal with the mechanical, there would be stress concentration. So how to deal with, can we modify those? Disc thickness, which is very much important, as well as effect of diameter on the spring. So quickly, let me drive you through flexure spring analysis. So this is the actual photograph of our photochemical each flexure spring, again, which shows, yeah, so periphery hole, this is the width of spiral cut, diameter, then PCD, there are around 12 holes, and 3 spiral arms, 1, 2, and 3. And this angle, which is being traversed, this is the spiral angle. And you can imagine the size as well, right? So this disc was used for further investigation, and how these spiral arms are supporting each other and how that design matters. Okay. So since we talked about single or individual flexure spring, because in cryocooler we need to have better stiffness, so we are using it in stack. So, and we are using linear electromagnetic drive, because these drives are employed into the aerospace applications, and they are frequently used to ensure reliable and maintenance-free operations, right? So this drive system uses electrical coils and are mounted on piston shaft, you can see here. And these are the stacks of flexure. This is electromagnetic drive system. And this coils rotates within the magnetic field created by the pole pieces, right? Through permanently magnetized axial magnet, without getting physical contact in the chamber. So again, like when we talk about stiffness, a single spiral spring would have stiffness is equal to K, but again, multiple stack would have total stiffness, right? Because our system, the main aim is to reduce the power needed for the linear motor. That's how we are also interested to calculate the resonance, so that we could also have, and this definitely is can be accomplished by designing the moving mass to resonate with the combined spring force. Because axial stiffness of the flexure spring is always lower than the gas bearing. Because see, even for this, the most important parameters are axial stiffness, radial stiffness, as well as fatigue strength. So how we can have? So alternative, we have applied strains, okay, to validate the even geometrical configuration. So you can see actual stacking, okay. Yes, this is also important, because moving forward, we have considered various geometrical features of various sizes, materials, and that has been also displayed on the board. So you can have a look. So all these things we have considered for experimental investigation, and through that experimental investigation, even we went up to ground, up to 100 mm of diameter, right? So you can see here, and you might be surprised to see the discoloration or something. So this is beryllium copper. It is very much prone to oxidation. So copper oxide gets formed, right? So that's how it happens. So now we will consider the most important, because the most important requirement for flexure springs are high fatigue strength, as I discussed, low axial stiffness, and high radial stiffness. So when flexure springs are stacked together, their stiffness increases due to their arrangement and interaction of the springs, and that can be definitely, that is going to add value to the weight and other stuff. So it is often challenging to perform precise theoretical analysis of flexure spring due to the combined loading and complex geometry they are subjected to. So in that case, what we have done, we used approach of numerical analysis. And since this is a non-linear statistic kind of problem, non-linear static structural problem, so we have used finite element analysis using ANSYS. Okay. So where we could exactly predict the behavior of the flexure spring under specified boundary condition. So that's how we have done extensive finite element analysis of this flexure spring. Because again, what is most important thing, the critical consideration for flexure is accurate prediction of spring behavior, identification of failure points, because there would be chances that this flexure gets failed at this particular, or crack propagation gets started, design optimization, and definitely cost, time, and savings. So in ANSYS, to perform non-linear static structural analysis, the first step is to create a FEA model, which is our objective number 1. And then this model is used to simulate the behavior of spring under different conditions. So considering those effects, geometric non-linearities, the displacement and stress at various points we have optimized, and we have employed again the general process, pre-processing, solution and post-processing. This is very much important. These two element types we have used for our FEA, hex 20 and weight 15. So hex 20 element with 20 nodes, you can see, right? So this element is capable of modeling both tensile and as well as compression, and it gets also subjected to shear, bending and torsion. And this wedge kind of element which is weight 15, it has 15 nodes. Again another 3D important element in ANSYS, which has 6 corner nodes and total 15 nodes. And it is also capable of subjecting to torsion as well as compression. Meshing. Meshing is very integral part of FEA to get started with, because it divides model into series of multiple nodes, interconnected elements, and which predicts the entire behavior, right? And the significance of applying boundary conditions to FEA in their ability will accurately simulate the real world scenario and behavior, right? So we also carried out mesh independence test initially only. So you can see normal mesh model and fine mesh model. So this test involves performing the same analysis multiple times with meshes of different sizes and comparing the results. Because the main idea is to determine the point which the results of analysis are not sensitive to the size of the mesh. Because if it gets sensitive, it shall be independent, right? Because in stress analysis, discretization matters a lot, and this mesh independence shall not be influenced by the discretization of the model, okay? So that's how we have to converge with the solution. So mesh independence test match. So this table shows you the readings where nodes and elements have been changed and the values also. So it is observed that results are very much consistent throughout. You can see up to 0.5% variation. Even that was for stress analysis. Even we carried out mesh independence for modal analysis. Okay. So it shows the solution. So from this mesh independence test, what we can conclude, the solution obtained is independent of the mesh size, the chosen mesh size is appropriate, the solution reaches to near steady state, and the error is within acceptable range. So after that, now we started doing detailed parametric investigation of each and every parameter. So first is geometry. So for geometry, as I mentioned earlier in literature also, we have done exhaustive literature review. So various sorts of geometry we have undertaken for investigation. Like in first mesh model, what is equivalent stress and deformation subject to the same 1 Newton load and specified boundary condition. Then another sort of flexure, what would be the value, right? So let's understand this. What would the impact on deformation as well as stress value and strain value? Then another geometry like this single arm, right? What are the values? And likewise. So we came to conclusion that this 3 spiral arm, the equivalent stress and deformation. So because the requirement for us, low stress, maximum radial stiffness and less axial stiffness so that it can flex. Then we considered number of spiral arms. So we have chosen Archimedean as a geometry. So on this screen you can see 2 spiral arms, 3 spiral arms and 4 spiral arms. And what would be these are all deformation values, right? So it is worth noting here that the relationship between number of spiral arms and the performance of the spring is not required to be linear. There shall be trade-off between the same, because adding more number of spiral arms will remove the material, and material, if it gets removed, then again it will not always result in the proportionate requirement in its load carrying and deflection possibilities. Then width of cut. So even we tried 0.4, 0.6, 0.8, 1, but again as far as manufacturing challenges, we can't go up to 0.4 mm because of the intricacies and other. But still you can see the values of stress, right? Because a narrower cut definitely may result in lesser or but again we need to find the trade-off between the number of spiral arms. Okay. Then angle of rotation or spiral angle. So again, we have done multiple, right from 360, 420, 480, 540, 560, 570 degree. Because a steeper angle definitely results spring with higher radial stiffness, while shallower angle may be more suitable for applications where low axial stiffness is required. Okay. But in general, larger spiral sweeping angle results with the better stiffness requirement. Then modification of the areas, like here you can see end point geometries of the flexure, right? So the design of flexure spring towards the end of the flexure spring resulted in high stress concentration area because of, again, geometrical features. So to reduce, because there are more chances where your flexure spring will get failed. Okay. So to reduce, what we have done, we have modified the end point geometry. As you can see from A, this is normal cut, then we have modified like this, then what is the value, then like this and like this. So it is observed that shift to end point geometry did not definitely reduce the width of cut, right? But it will come to the sweep angle where it is directed to the innermost curvature. Okay. And it is also obtained that beyond this geometry endpoints fix and finalize, this design feature could have better stress relief. You can see here for A what is the stress value and for D. Okay. So this is how we modified the stress concentrate. Then very important parameter, disc thickness. So thickness of disc used in flexure spring influences its performance because thicker disc may result in spring with higher radial stiffness. You can see here 0.5, 0.7, 1 and 1.25. And what was the difference? In all the cases we have kept spiral arms is equal to 3. So also all being equal, spring with thicker disc has large cross section area. So definitely it would be more stiffer than the lower value of this or thinner disc. But again, we have to come to the trade-off where we can also investigate according to the manufacturing feasibility. Then effect of diameter. So again, you can see multiple, it has been displayed there also. So this is flexure spring with diameter of 45 mm, 69 and 100. So it has, because larger diameter may result in spring with higher radial stiffness, but it is going to have low axial stiffness because it will be more stiff, right? So according to the applications we have to. Then another most important milestone in this project is selection of material. How to conclude about the material of this flexure spring, right? Because it is very much critical factor and it should have high fatigue resistance subjected to numerous loading and unloading cycle because continuous bending and other stuff it is going to withstand. So to assist in material selection process, we have used standard HB chart, again very much available on the ANSYS resources website. And here we considered 6 different material options. And those material options are also displayed over there, like AISI SS302, AISI SS304, then beryllium copper 17000, beryllium copper 17200, TH, which is heat treated. We have also used grade 5 titanium and Amcoloy 944 alloy. And this analysis consider various physical as well as geometrical like parameters which we discussed. So these are the material properties of the 6 different options, SS302, 304, right? Beryllium copper, and you can see the major properties which we discussed, ultimate tensile strength, right? And percentage elongation. So based on these inputs, we have started, same inputs we have provided to ANSYS library. And then we started analyzing each and every material, right? So stress value. So this for SS302, it shows stress of 319.59 MPa, deformation around 0.46, and stiffness is around 2164103. For 304 again, which exhibits the value of stress 339.27 MPa and 0.45 as a deformation, right? Stiffness we can easily calculate, okay? force upon. Then beryllium copper 17200 heat treated. It exhibits very low stress, that is 305.99 MPa, and deformation, maximum deformation, right? So likewise we have done. Now come to the manufacturing feasibility. So all of the 6 material which we shortlisted based on various iterations, because we can't compromise significantly on their material properties, right? So SS 302 and 304 are both types of SS which can be easily formed. And all these shortlisted material can be easily formed into thin sheets, right? And but beryllium copper being strong corrosion resistant alloy, again titanium is very strong, but again for machining it would be difficult. We will discuss that also. So let's discuss one by one what challenges we faced for selection of SS. Like for stainless steel, the most important challenge which we encountered when working with SS 302 and 4, formation of burrs, you can see here. And I do have also samples, right? So it shows irregularity while cutting through the intricate shapes and profile curves. And these burrs negatively impact the fit and function. Even if you go for deburring operation post-processing, still it will reduce the, and it will add up in the cost as well as time. Then another challenge confronted while working with SS is HAZ, heat affected zone. You can see. So because of that, whole material properties gets changed, right? Because these are the areas which is subjected to high thermal stresses during plasma machining or laser cut machining. Again, cracking and weakening because of the carbon percentage. Then another challenge is warping. So when this will subjected to high heat and other, definitely it will tend to warp the thin material. So if it get warped, then how to stack it, right? Then what challenges we encountered with titanium 5? So again, there are several challenges stumbled upon, but machining thin metallic disc from grade 5 titanium is next to tedious task, because when we work in microns or even the tools which we will be using for working on titanium, those tools will get itself failed. They are very much cut and prone to tool failure. And even tendency of titanium to stick to cutting tools lead to clogging as well as reduced accuracy. So that is also difficult. And another challenge with the titanium is it is very much prone to oxidation. So we can't, once it will get interfered with the laser beam machining or laser processing, high pulse rate and other stuff, it will be prone to. Then what challenges about the Amcoloy 944 alloy which we use? See, there are several challenges in the context of photochemical etching, because Amcoloy 944 is again high strength and hard alloy, right, which requires higher etching rate, which adds time and other thing. And again, to work on that, we have to apply protective coating on that. Then only we could process with the. And another challenge with the Amcoloy 944 is, after etching, you will get surface roughness in very much what we can say, which is not acceptable, and again we have to go for post-processing. And out of these other materials, if we talk about beryllium copper alloy which we use, it is very soft material and it is very much easier to etch it using traditional photochemical etching process, which can be manufactured by even the trophy makers and other stuff, right? So that's how these all unique properties and other stuff, we found it well suited, right? So again, why beryllium copper? So we have come to the conclusion, because we need to also ensure it shall not fail during the mission life analysis. Yeah, so then we have gone for the parametric analysis once material has been finalized. Like we consider, we have fixed this, and now number of spiral arms has been varied. So 2, 3, 4, and again, to our surprise, all these 3 variations are subjected to 1 Newton load, right? So this is the result graph where you can see what happens when we select 2 as number of spiral arms, 3 and 4. You can see stress values and stiffness. So these iterations helped us to find out the effect of number of spiral arms on stress distribution, right? But it also increases the spring's overall size and weight, because if we go for number of spiral arms, definitely material will get removed, then load carrying capacity will get also. So we have to find the trade-off. So considering here minimum stress and maximum stiffness criteria, we selected this 3 as a number of spiral arms, which exhibits 305.99 MPa and stiffness of 1451.44 Newton per meter, right? Then we considered about the spiral cut, width of spiral cut. As you can see, 0.2, 0.4, 0.6, 0.81. But again, as far as manufacturing feasibility, we can't go 0.2 or 0.4, though we could have better or close values, right? So we have to consider those things as well. And this is the graph where you can see 0.2, 0.4, 0.6, and so you get the linear one. So again, in this, it is pretty clear that we can have width of cut as 0.6, where we can get the lower equivalent stress and maximum stiffness criteria. Then spiral angle, as we discussed earlier, 360, 420, 480. So again, you please refer to the values, right? So I'll quickly show the graph as well, so that it would be better too. So if we have various parameters, various values for the spiral angles, you can see the best suitable combination comes around this 560 degree. It seems more suitable, which again exhibits stress value of 305.99 and stiffness as 1451.59 Newton per meter, right? Then another important factor is disc thickness, because this thickness is very much responsible for the resisting bending forces which our flexure spring is going to get subjected, right? So again, we plotted the results to understand, to finalize. So optimal thickness for flexure spring disc is very much required, which could result and which we could get the possibly minimum stress as well as maximum strain. So 0.7 seems to be better option considering this, right? So based on all these finite element analysis iterations and outcomes, we finalized this FEA model, and then the second objective is being achieved. So how to fix the best suitable geometrical configuration, okay? Which like your flexure spring could have sufficient stiffness, lower stress requirement, as well as infinite fatigue life. So we considered 3 as number of spiral arms, width of cut 0.6 mm, spiral angle value 560 degree, and disc thickness as 0.7 mm. Now for different strokes, we also considered stress and stress calculation from 1 to 5 mm for different strokes. And so for space application, which we talk about a free piston, free displacer, 5 mm stroke is sufficient based on the literature and other stuff. So we considered it for 5 mm stroke, and for each stroke we consider same. So what happens with plus minus 2 mm stroke, right? 3 mm, 4 mm, okay, 5 mm. Okay. Then we have calculated stiffness analytically. So it is because both axial and radial stiffness are very much significant as far as design of flexure springs are concerned. And it shows non-linearity, right? So non-linearity refers to the property of material. So based on that, we have find out stiffness coefficient, and then we proceed further. Then we carried out modal analysis using FEA. See, modal analysis is a technique which used to determine the natural frequency, mode shapes, damping ratios of system, and it is particularly useful for understanding the performance behavior of the flexure spring, right? Because it helps us to predict the response of flexure spring under various excitation frequency, how it will act, how it will perform. So you can see in table which I have shown for beryllium copper, first mode and disc thickness. So if I vary disc thickness value, natural frequency also varies. So stiffness of spring is also being increased. So this graph result will show you the correlation between disc thickness and natural frequency for different material, the shortlisted materials which we have shortlisted, right from SS3022 to amcolloy. So it is very much obvious from this graph that thickness of disc increases, the natural frequency of the flexure spring increases too. And this is because the thickness of disc increases the stiffness, which also results in higher natural frequency. So it matters a lot while choosing resonance and other. So how we can, and most of you might be knowing the direct relationship between the thickness of the disc, because when we are talking about frequency, it can be found. Then we have also done modal analysis of our fatigue life setup. Now there is a twist because we have considered it for two cases. First case is considering with magnet, because we do have linear motor with the magnet, which is strong magnet. And if we talk about linear motor, which is having around magnetic flux density of 0.8 Tesla, right? So we have to also consider same while doing the analysis. So we have considered magnet first, and then we have considered without magnet, right? So you can see the values of frequency for 2 flexures, for 4 flexures, for 6, for 8. So flexures are at both the ends. So we have taken different combination, 2, 4, 6 and 8, with magnet and without magnet, so that we can understand the importance, because magnet is going to change it affects a lot, right? And this is without considering magnet. Okay. So for 2 flexures, 4 flexures. Okay. So this is just casing. Then we proceed ahead towards fatigue life analysis. Why it is important? Because it defines the life of the flexure spring subjected to the mission life. So it is very much essential for us to consider, and on screen you can see for various disc thicknesses and various materials what is the fatigue life, and what about the selected material as well. So flexure spring experience cycle of loading from no deflection to 5 mm like we discussed right now. So when flexure is at its central position and has deflection, right? So deflection increases with the stroke as well, right? So this leads to limiting the stress value, and that's how you can see. But to our surprise also, for beryllium copper 17200 heat treated material, even for 0.3, 0.5, 0.7, you are getting 10 to the power 8 cycle as fatigue life cycle. And this is the very much requirement of our cryocoolers to have infinite fatigue life, right? So we have used even titanium and amcolloy also shows, but again for titanium 0.3, right? So limitations are there. So once we are satisfied with the FEA iterations and analytical process, we went for experimental investigation and validation, which involves testing spring under various loading conditions so that we could determine their axial stiffness, strain as well as fatigue life. So this is very easy setup. So for objective 5 to design and develop test kit. So axial stiffness, which is also known as longitudinal. So we have used simple dial gauge. When the load increases, the dial gauge indicates the deflection and deformation, right, along to its longitudinal axis. And this graph will show you the relation between experimental and analytical stiffness which we have found. So average axial stiffness value found to be around 1460.25 Newton per meter for the optimized geometry of the flexure spring made from beryllium copper 17200Th material with 0.7 mm thickness. So this graph establishes the comparison between experimental and analytical, and you can see slight variation again which is very negligible. So that's how we validate our axial stiffness. Then we went for strain measurement. So for strain measurement again we have to use strain gauges, which measures the deformation of flexure spring under the load. And to measure the strain gauge is typically, you can see, attached on the flexure spring surface. So which measures the resistance of the gauge as the strain when the spring deforms. Okay. So as metal foil gauge gets deformed, the values, and these gauges are very inexpensive but very high sensitive. So we have to be very much careful. We have to take readings multiple times without all these external parameters. So based on that, we have carried out, we have used various adhesives and other. So experimental strain was calculated as well as analytical strain. Both were compared later on. The most important is fatigue life validation. So to determine fatigue life of flexure, when it is subjected to repeated loading and bending, we have fabricated this fatigue life setup, right? And this setup is very much required for dynamic loading conditions where we can simulate actual environment and do the testing. So here you can see various components like supporting members, flexure mounting, shaft, coil former, magnet, flexure stack, mounting, right? We have also taken cross-section view so that we could have better idea about linear motor cross-section as well as bill of material. And this is 3D rendered model before we proceed. So both exploded and other view. And this you will understand from this explosion view how this setup is being manufactured and assembled over here. Okay. So this is actual fatigue life setup. So we have used electric supply frequency which is set to 50 Hertz so that we can have standard frequency for determining number of cycles. And the system is run average up 400 to 500 minutes per day. So we have run this setup almost 80 days for space application, right? And under the monitoring and observation. So almost to achieve the 50 Hertz, to achieve the 10 to the power 8 cycles. Okay. So you can see here flexure stacks and other. Even I am going to show you the demonstration. Okay. So based on all these things, we have results and other, the data which we have taken from testing. We created a graph which is very important graph for fatigue life testing, that is SN curve, which gives us the relationship between stress range and the number of cycles to failure, right? And which helps us to estimate how many load cycles your flexure spring can withstand without material failure. Okay, so this curve as shown in figure will help you to identify for various materials. Of course, we have done for beryllium, copper, SS302, titanium alloy, amcolloy, right? So additionally here you can see beryllium, copper. So it shows a unique combination of low and high cycle fatigue performance. So which means that high cycle performance can be very much possible. Then we also done natural frequency, that is modal analysis estimation. So using FFT analyzer. So flexure spring is mounted on the flexure mounting plate, right? Such as sinusoidal force, and the response of the spring is then measured using the sensor, that is accelerometers. So once it has been done, the readings have been captured. So this is how it's set up. Accelerometer is mounted on the shaft of the setup and the supply cable is connected to the AC mains. And known excitation force is applied to the flexure spring which is mounted and affixed to the test setup. Again we did this with magnet, without magnet at actual setup. Okay. So yeah. So these are the frequency response which we obtained using fast Fourier transform. So here you can see the peak, okay, which shows, and this has been done for number of flexures is equal to 2, where 13.67 Hertz indicates that particular frequency or set of frequency present, and 0.436 here you can see G, it indicates the amplitude level and the signal being analyzed. So similarly we carried out same for flexure spring is equal, where we have 4 flexure springs, then 6, and then 8. Again, you can see for 8, 27.83 hertz, right? So system with more flexure has higher natural frequency than the system with fewer flexures, because we have done it for say 2, 4, 6, 8, or even other combination. So this can be definitely understood by simple law of conservation of energy, right? So as the number of flexure in stack increases, natural frequency also increases. So again, you can see number of flexure using FFT, without magnet, analytical, without magnet, experimental, again. So comparative results are tabulated here. And again, graphs have been plotted to understand the relationship between experimental as well as analytical. Results and discussion. So these are very important point, because based on results for 2, 3, 4 we have carried out. So we would like to find the correlation between spiral angle and natural frequency, because natural frequency, since our main objective was also for modal analysis. So this graph illustrates when the spiral angle increases, the natural frequency decreases, right? And change in natural frequency is more pronounced with an increase in the spiral angle. So this implies that as spiral angle increases, natural frequency decreases and the number of arm increases. Another important graph is correlation between spiral angle and axial stiffness. So again, typically if spiral angle increases, the axial stiffness of the spring decreases. And why? This is because of the larger spiral angle results in more material removed, right? Then correlation between spiral angle and radial stiffness. So again, the graph is plotted, and you can see as the stiffness of the spring changes, the spiral angle is varied with respect to the radial direction, and with the same with the case of radial stiffness. Then we have taken the ratio, correlation between spiral angle and the stiffness ratio, that is Kr by K, radial stiffness by axial stiffness. Again, you can see the graph. Yes, and correlation between spiral angle and maximum von Mises stress. So maximum induced stresses are necessary for our design parameters, and it also shows, this graph shows when stresses decrease exponentially as the spiral angle increases and the number of arm increases. Okay. So what it means? So it means by increasing the spiral angle or the number of arms, the stress on the spring can be reduced, which can lead to longer spring life and better performance. So quickly I would like to summarize. So theoretical, analytical, experimental axial stiffness values are found around 1495 Newton per meter, 1451.45 Newton meter and 1460.25 Newton per meter respectively. The difference between theoretical and analytical values is around 4.5%, and the difference between theoretical and experimental values is around 2.5% for axial stiffness. And this result suggests theoretical values are in good agreement. Then as we discussed about modification of areas with higher stress concentration. So again, modification in the endpoint geometry would almost help us to reduce up to 22% in comparison with the normal. Then strain in flexure spring is measured experimentally, and the difference again is around 3 to 7%. Again, it shows very close match. Conclusion. So this parametric investigation study, it finds that 3 spiral arms has the maximum deflection and minimum stress for a given condition. So the additional spiral arms in flexure spring provides less support for the load, allowing spring to deform more and support lesser load, right? But again, as we need to find trade-off, it is not linear relationship. It is also worth noting that width of spiral cut needs to be considered in conjunction with number of spiral arms and disc thickness. The most important parameter is spiral angle and disc thickness for flexure spring performance and analysis. So according to, we have to Again, but material, we have to find the trade-off. Again, we found out that smaller spiral angle results in spring with tighter radius of curvature because the innermost, because of this. But again, we can also find the trade-off. It is also observed that larger diameter flexure spring have higher spring constant because of the force exert and allowing longer strain. But on the other hand, smaller diameter for space application as discussed have lower spring constant and exert less force on pistons, okay, resulting in shorter stroke. So FEA results of the flexure spiral spring model frequencies are verified, validated by comparing first 6 modes, right? And which shows disk thickness is increases with the modal thickness. And it confirms our modal frequencies predicted by FEA analysis are accurate, and the material and disk thickness have an impact on the modal frequency of the spiral flexure spring. And last but not the least, the fatigue life of the flexure spring for various materials and disk thicknesses varying from 0.3 to 1.25 mm determined through FEA, then validated using fatigue life setup, shows that flexure spring exhibits infinite life at 10 to the power 8 cycles. So what could be the recommendation or future scope? One potential area of application of this flexure spring could be in Stirling engine for ground applications, where we could have different configuration based on the, and we could optimize the stack assembly as well based on the application, considering the overall stiffness requirement. And this can also help us to ensure that linear compressor operates efficiently and reliably over a longer period of life. Another could be like fatigue life testing involves evaluating durability of this flexure, right, of different geometrical configuration. So we could have modular arrangement where using single fatigue life setup, we can test multiple geometries and other things. And that can be also patented work. So before I conclude, I would also like to showcase dashboard which I made using Google Data Studio with permission of PDC members. Okay. So this dashboard has been made using the various data points because we have carried out around millions of iterations using FEA for various geometries, So for this, like axial stiffness, as I mentioned. So here you can see using this dashboard, let me minimize this, yeah. So you have to just select the weight in pan, and you will get the required results for these geometrical features, right? And you can also have material and spiral arms variation for space application. So you have to just select the variable, those who would like to take this research ahead. So I have done it for these 7 different material options: cold-drawn, beryllium, copper, grade 5 titanium, amcolloy. So if I select amcolloy, you will get the graphs as well as results for stress values, deformation, and stiffness, right? Even you can select the number of spiral arms, and you will get the results about deformation and disk thickness and others. Now I am also working for the graphs and the results, so that it will also get mapped based on the variation, and you will get the real-time results. Yeah. So let me get back to my presentation. 1 second. Yes. So thank you. I would like to express my sincere thanks, right, to Research and Consultancy Cell for generous funding and the opportunity. These are the publications I could make throughout this research study, around 6 publications. All of them are Scopus and SCI index publications. And the accomplishment throughout this journey. So the project titled, we have got first prize in national level I2A Academia Pavilion at Indian Machine Tool Manufacturers Association IMTEX, which is Asia's largest machine tool expo in 2019. We got first prize for our So we have been awarded and we have also received appreciation certificate. Another accomplishment is one of the research paper titled which I presented in Springer conference, international conference, modal analysis of special, was selected as best paper and received best paper award which was conducted at GH Raisani College. So that's it from my end. Thank you, and the forum is open for questions.
Right. अभी हो रहा है. Okay, so thank you for the presentation and congratulate you for the presentation that you have done and all the papers and awards that you have received. Now we will open this Viva for question and answer, and we will first start with our external examiner, followed by internal examiner, and then it will be open for all the members who are present offline here in the room, and then the offline people who are present. So I request sir to please start with the question.
Yeah, your work requires so much of effort, which we can see it through your entire presentation. You first of all completed your study on the flexure bearings. This is first thing you have done. Then you have went to for a kind of a geometric variation, and you have conducted an FEA analysis. And then you have done a parametric analysis where you have changed the different parameters of flexures. You have studied how much amount of stresses it is generated, what will be its fatigue life, what will be the stiffness variation, all these parameters. And also you have conducted a modal analysis in FEA. And these experiments, whatever this theoretical or numerical study you have conducted, that you have supported with your experimental setup also. And at the end, it was very appreciable and good database you have tried to create using a data that is Google Data Studio. So I would like to ask one in this case in Studio, is it your data, whenever you are going to do any kind of analysis, will it take an interpolation between the points, or will it be only for a fixed number of data points?
Thank you, sir, for this question. So it will not take the data which I fed, it will seek data from that only. So I have to input the results which I have got, that results will be only fetched. It
Okay.
will not calculate by itself.
Okay.
Yes,
So
sir.
that is the only thing it does.
Yes.
So another question, you have done an FE analysis, exhaustive FE analysis, and
Yes.
you have done a very much, very huge analysis part of it. I would like to ask you, because you have somewhere mentioned that you've done a non-linear analysis of FE. What are the kind of non-linearities you have taken into count?
Sir, considering flexure spring geometry, it has various surface non-linearity and other stuff.
Okay.
So to model exact flexure spring in FEA, it would be difficult. That's why in FEA we considered non-linear static structural analysis, and accordingly we we selected the inputs for an analysis further and we took it forward.
So have you considered that there is one option in the FEA, answers analysis? Have you opened that option like a large deformation on or something?
No, sir.
Okay. Another one, it is expected that your stress, whatever the stiffness, axial stiffness should be within the range 1400 to 1500 something, and radial stiffness 17,000 and something. Why you have decided these numbers, and why you are expecting your flexure should have, and a single flexure should have the stiffness in this range?
Thank you, sir. So, based on the factor of safety calculations and mission life, we came to the range so that it should not fail. And sometimes catastrophic failures no one can expect. So, considering all these limits, we have fixed this range.
This range was you have deduced from literature?
Yes, sir.
Okay. And another one, you have decided radial stiffness should be somewhere 17,000 and more. So is there any specific reason for this?
Yes, sir. Because when we talk about cryocooler, it has clearance gap of only 15 micron, right? And it shall not rub the seals, clearance seals. So considering 15 micron gap on the surface, we shall not go beyond certain limit of this radial stiffness as well.
Okay.
So that's how we have also deduced that through empirical relation.
Okay. Have you anywhere observed when you are keeping your entire setup in horizontal state? So obviously weight will come into the picture.
Yes,
okay?
sir.
And most of the time you may be orienting your compressor or cryocooler in horizontal direction. So in that case, weight may come into the picture, and that may reduce the gap at the lower side of your motor. So have you taken account of it?
Sir, that definitely needs to be taken account for ground applications.
Okay.
But for space applications, since this is going to be at the end where almost ambient temperature, flexure springs will be in ambient temperature.
Okay.
So as far as space applications, that is not required to be accounted. But definitely for ground application, it has to be considered based on the.
Okay. So
Gravity will not be there in space.
Yes.
You keep it horizontally.
Yes.
okay.
But for ground, definitely we have to consider that.
Yeah. So because it is also used in compressor in many places.
Yes.
Another one, you have worked on the damping frequency
Yes, sir.
calculation. Experimental frequency also you have done, and FEA, that is natural frequency also. So can you tell me what is the amount of damping frequency you have determined? Have you determined any damping frequency?
No, sir. So what we have done, we have used dampers for actual fatigue life setup.
Okay.
In any way, ANSYS, we will get the results. But for actual fatigue life setups, when even we use FFT when we are giving stroke, so we have ensured that the we have first we have taken it on surface plate, right? And then we have taken care that it shall not have own damping. So we have used dampers, rubber mats, and other stuff.
Okay.
Yes.
So can you come down to your slide number 131?
Okay. Yes.
One three one.
131. Okay.
Ah. So it's, I think somewhere 131. Yeah, go back. Summary of the before that. Somewhere there was in a graph of showing frequency and your number of I think spirals.
Flexures.
Yeah. 121 I think. 130.
Okay.
129 something. Yeah, that one was odd. I would like to know why it is like this.
Got it, sir. Got it.
Yeah,
This-
the same.
Yeah.
129.
So definitely. Let me tell you. So this results for spiral angle for correlation, establishing correlation between spiral angle as well as stiffness ratio. Stiffness ratio is the ratio of radial stiffness to axial stiffness, right? So in case of where we have two spiral arms, this variation is possibly because of the stiffness of that two spiral arm. Because when we have only two arms, it will be more stiffer than spiral arm 3 and 4. So that's how This graph goes like this
Okay,
because of the ratio which we have taken.
Is there any strain hardening or something it is going to happen?
No, actually, in that case, radial stiffness is much higher.
Oh, okay. That
So,
happens to be
हाँ.
540 angle
Yes,
and
yes.
that is the two number of arms. Okay. Is it any connection within a geometry or something?
Yes, sir. Definitely, geometry is also going to affect.
Means
Yes.
maybe some problem with geometry that if I'm going for only two arm flexure. Okay. And last one you said that Carnot efficiency was in a somewhere 55%.
Ah.
Okay. So what is in a Stirling cycle efficiency? Is it in a 55 or less or more?
It is in same range, sir.
Okay, same range. Stirling will be in the same as in a Carnot cycle efficiency. Okay. So as of now, I have finished my questions and I will hand over it to Madam to continue for further question and answers.
One question is there. Your
On. Huh.
So you have cited number of applications in first few slides. So have you studied or done any literature survey? What are the sizes? I mean the diameters for all these applications. It will vary, I mean.
No. So, for other applications, I have not done literature review, sir. But for space applications and ground, like there was one project with BARC as well as ONGC. So, but for other applications like tactical defense and other stuff or biomedical, I haven't done literature review for that.
For space application, what were the sizes in literature review?
So, it's right from 35 mm to 45, even 69, up to 69 mm.
Okay. And in your case?
69 mm.
69. Okay. All right.
Thank you, sir.
Okay. Anyone here in offline mode can ask questions.
One more thing, I mean, you have done that dashboard thing beautifully. So, and you said that the data which you have given, that will be only fetched. So, is there any option the user it will do the interpolation so that the data in between can be fetched?
No, sir, that is not recommended because all those data has been has come as an outcome of from FEA. So since I have done exhaustive iterations, I do have Excels and data sets ready with me. So accordingly, you can choose the combination. You can have more than 3,000 combinations from that data set and you can find out the answers. But beyond that, again, we have to provide data.
Let me congratulate you at the outset for a good presentation for which MIT ADT University knows you. I'm not a mechanical engineer, let me admit that. I am just trying to ask what I understood. The fact that you have done an exhaustive parametric study and yes, all that has been presented and the results are there. But I wonder, I don't know whether it's possible or not, or were it not possible for you to develop a kind of a model or a relationship, because it was a parametric study. And what I understood is not, probably you're all, that particular component which you're talking about, the functional requirement is the diameter, because normally that is fixed probably and the rest of the parameters would depend on that.
Yes.
So, although you have a dashboard which you said and there are limitations of that dashboard as you commented, was it not possible for you to develop some kind of relationship which would give for a given diameter of the spring, what are the other possible like thickness, the deformation that is to be permitted, etc. Could you not provide that kind of information or that kind of equation or develop that kind of equation in your thesis?
Definitely, sir. But considering the requirement, thickness and other stuff, weight requirement, since our space application, that much variations is not required. That's how the data which is very much required for cryocooler for a particular application, we have fetched all this and we have developed that parametric model. But definitely, as you said, it can be done further and it can be taken ahead with the help of master scholars in future.
Question is, you had shown us the graphs of spiral angle versus natural frequency, spiral angle versus axial stiffness, spiral angle versus radial stiffness. Except one, I think I couldn't see any optimum points in those. So all those parameters, of course, every work has limitations of time, money, and everything. But don't you think that you could have got some optimum points which would have said, yeah, this is the right thing?
Yes, sir. We do have optimum. Let me just show you one sample graph so that. Yeah. So if we consider this correlation between spiral angle and axial stiffness, simple. So by doing this exhaustive iteration and other stuff, what we came to know, because we have considered around 6 to 7 parameters which are very much critical for flexure spring design, right? But in that, I have also come to the conclusion that which is the most critical parameter in this. So like this thickness, spiral angle. These two are very much important because once you change this dimension or value, whole things will get changed. So accordingly, we have optimized this, and now on this also, that's what I am saying. Spiral arm, which is having 3, this is the optimal value, which we shall consider, which shows less axial stiffness, and that is our requirement. We shall have less axial stiffness, high radial stiffness, minimum stress. So these are the requirement for cryocooler applications in space. So that's how we optimize.
Okay. And is there anything like what you call the minimum thickness and the maximum thickness that you could recommend from your work?
Yes, sir. So basically, minimum thickness can't go less than 0.6, 0.5 because of the manufacturing capabilities and other stuff. Definitely you can go for milling and other operation, but in that case, this thin metallic disc will get warped, which will not of use. And as far as maximum thickness, it is not recommended because if thickness will get increased, it will become stiff. Then we will not get axial stiffness value. So that's how we came to the conclusion that 0.7 mm could be the best thickness for our application, and we have come to the conclusion.
Thank you.
So it's always trade-off. There is no linear relationship.
Anyone else?
Yeah, let me open forum those who have joined online. 1 second.
Sir, we have here first offline.
She will
I'll do that. First we'll go for offline mode and then we will ask the
Okay.
questions. So, sir is there.
All right, so thanks, Suraj, for this wonderful presentation, and I congratulate you for the very deep work that you have done. I think if you were able to establish a variation of 2.5% with regards to your theoretical and your experimental work, I think all the processes probably, while you were doing the 4.5% deviation in the analytical side, is kind of covers all of that aspect, right? But my basic question, as I appreciate the theoretical work and the effort that has phenomenally gone into this whole doctoral work, how do you see this application? And you kept on speaking about the space application for this. So what specific space application that you think you want to target this for?
So for cooling IR sensors.
Okay, so for cooling IR sensors, who are the players right now who are using this, or an alternate to this for cooling the IR sensors?
So right from Thales, cryogenics, there are a lot of players.
India में कोई है क्या?
Yes, sir.
Indian player है क्या कोई?
No, sir.
Okay.
European player.
European players, and all of this is being imported by ISRO. Space ISRO ही करेगा और तो कोई करेगा नहीं.
Yes.
Okay, so if ISRO is importing all of that, and there is this piece that goes into those cryo coolers,
Yes.
Which is again well studied, well documented. Is there an opportunity for taking over that space where we can push this out to ISRO and say, okay, this is what we have done in the lab? Does it make sense for replacing the current system that is being placed into the cryocoolers for cooling of the IR sensors and generating revenue out of the work that you have kind of done?
Yes, sir. So around 2017-18, the funding has been received from Space Technology Cell, Savitribai Phule, Pune University, and the same work has been continued, and it is extension of those work. So that has been also presented, and this report is also being presented because the sanction
So
has
the
been
funding came to you?
to my guide.
Oh, acha, the
My,
funding from
my-
SPPU has
yes,
come
my
for
research
this one.
supervisor. Yes.
Okay, and now that funding has resulted into this stage of where we
Yes,
are
yes.
right now. And
So we'll be also submitting our report post this with the ISRO officials as well. So
yeah,
that
because
we
to
can-
me, I mean, there are only two critical elements to this whole work that you have done. One is the design,
Yes.
and second is the material,
Yes. Sir.
right? With all permutation and combination within the design elements, those metrics that you kind of played around with, that still results into some design, right? If design is unique, can we go ahead and do the design registration for that unique design, if that's unique? That can give us one edge. Or if material is something that we have kind of found out that this is a material, or even the combination of that, right? So does that present us an opportunity for taking this PhD work and converting into something which kind of becomes like a pioneering attempt for our
Yes, sir. So
gift to the ISRO probably?
definitely. So for material, let me share this development. When we went to, means every year for last 5 years, I have been visiting to Indian Machine Tool Expo, which is held in Bangalore at BIC. So the main intention to collaborate another. So in 2018 itself, we came across Amco which Amco Metal Limited, which is again Pune-based industry. They are into copper-based alloys for various applications, right from healthcare to medical and other stuff. So that's how also that Amco alloy 944 comes from that. They also helped us for the samples and other stuff, and that's how we taken. And we also requested them that can it be possible to change the material composition and other stuff. But again, at large, it's
मतलब ये beryllium copper ऐसा यूज हो रहा है इस उसके लिए भी या नहीं हो रहा है?
yes sir,
हो रहा है
बहुत
ना?
चीजों के लिए yes.
हाँ, तो वो मतलब अगर
For
इस
aerospace, numerous applications.
no, for this flexure spring or for the cryo application,
Yes, yes.
is that material being used or not?
Yes, yes, it is being used. Our intention or our try would be like, can we make changes like in using heat treatment process? Definitely, we could change the material properties or physical properties. Can it be another process where we can also have even this is not part because I have tried and tested out. I have also got samples manufactured using additive manufacturing where we have used copper alloys using Mark Forge machine metal 3D printer. We also got some samples, but again being very soft and ductile material, it will not sustain even I must say 10 or 12 cycles. So we have also tried to do that. Where can we challenge that using additive manufacturing after even sintering? I am talking about. So these are some challenges, but using material and other, definitely we could explore the area.
No, brilliant work. So once again, congratulations and for this in-depth work that you have done. I would like to see that to probably take it forward and get some funding, phenomenal funding to convert this into, as I said, the gift to the ISRO probably.
Thank
So
you. sir.
thank you for
Thank
that.
you so much, sir. Thank you. Sir. We tried using FRP, ABS and other materials as well, but it doesn't much long that up to 300 cycles, 400 cycles it will get failed. And again, if you go for carbon fiber and other, again manufacturing challenges would be there. So, yeah. Yeah, yeah. But again, but for that particular application, it would be difficult. Space application, which we are. Yes, yes, definitely. But it shall sustain to 10 to the power 8 cycles. That is what is required. 10 to the power 8 cycles. Yes, infinite fatigue life.
So use mic.
No, no. No. Can't.
Anyone else? Okay. Anyone from the online audience who wants to ask any questions, you can please ask.
1 second. Let me just allow them. Yeah. So I have allowed mic for every participant, those who join online. If anyone would like to add something, please, or ask any question. Yes, sir. Because unnecessary disturbance. Yes, anyone, those who join online, anyone would like to say something? Anyone would like to ask any question? Yes, Dr. Gokhale, sir.
Yeah. Good afternoon, Suraj. Excellent
Good afternoon, sir.
presentation.
Thank
I
you,
am
sir.
from the aerospace, so I could appreciate whatever you were saying, Two things, beryllium copper is no surprise, because that is one of the lightest material, and from the stiffness and the spring constant, this would be a terrific material. One thing, that I wanted to ask you, is that if you talk about the fatigue cycle depends on the vibration and mechanical plus the thermal cycling of the stresses, right? Now here you probably would have been able to do the mechanical, but have you given any thought to the thermal cycling? Because if it is a space application, are you thinking about a very fixed type of a temperature, or you are talking about a variation in the temperatures?
Yes, sir. I have given this thought, and we had several brainstorming session. But considering the application, these flexures are placed at the end of the displacer, which is having around ambient temperature kind of situation in space as well. That's how we haven't gone into so deep, because there is no that much temperature variation is.
Yeah, I mean, I understand, that there is a environment management, even in the space, you want to shield it from the solar radiation as well as from extreme temperatures and so on and so forth. So to that effect, you are fixing it at the ambient temperature, something like 24 degrees or whatever, Okay. The second thing, is that do you see any application of this, the theme that you have developed over here, for the older generation modules, like I mean the accelerometers or the gyroscopes and so on and so forth, which also need a little bit of
Yes, yes.
sort of a stable platform, Do you see any application over there?
So we tried to have some retrofitting as well. I understand. So we tried also for some retrofitting options, but we would explore how we can incorporate the same.
Yeah. And then the final suggestion from my side, is that biomedical heart valves, etc., they also would be interested in having this type of a thing, One, for the sizing application. Two, as you put it, with the additive manufacturing and so on and so forth, you can use and configure any particular material, Congratulations. I appreciate the whole presentation, for the past hour and a half.
Thank you, sir. Thank you so much, sir.
I'm done.
Thank you, sir. Thank you so much for your blessings and gracing the Viva Voce. Thank you, sir. Yeah, anyone would like to ask? The forum is open for this.
Okay, so we assume that there are no questions left. Okay, So now that there are no questions left from the offline and online mode, and Mr. Suraj Bhoyar has given a wonderful presentation and defended all the questions successfully. So from behalf of MIT Edit University, as in chairman of PDC of Mr. Suraj Bhoyar, I recommend the Doctorate of Philosophy in Engineering to be awarded to Mr. Suraj Bhoyar.
Wow.
So congratulations, Dr. Suraj.
Thank you, ma'am. Thank you so much, ma'am.
I also congratulate Virendra Bhojwani sir and Dr. Sanap sir for guiding him so well and coming out with a wonderful product.
Thank you, ma'am. Thank you so much for your kind words.
Congratulations from my side, Dr. Suraj Bhoyar, and the most esteemed and expert guidance from Dr. Bhojwani and Dr. Sanap. I think it has been a wonderful work that has been come. And of course, I must say, as a faculty member, I think you must be fortunate to get good students also. And I think you were fortunate to get Suraj Bhoyar as a research scholar. And to know, all of us faculty members, we have plenty of ideas and thoughts, but unless you get a good student to take it forward, things may not happen. So again, congratulations to all the three people. Thank you. Yeah.
Now my phone call, I'll get some keys.
No, you will continue to have answer.
Normally, faculty want scholars, they don't report. The complaint is they don't report. And it's the other way around. It is not reporting. I will get keys from tomorrow.
Congratulations to Suraj and Bhojwani sir.
Thank you, sir.
As well as Sanap sir and entire your team. And I had been working in these lecturals from long time because when we are working together for one project for an ISRO with Bhojwani sir, we worked on these flexes. But whatever the work you have done it is an excellent.
Thank you, sir.
You need to keep it up in future also and create as anyway you have done one thing, that is a dashboard, okay? And that is nothing but in a starting point. You have started, you are giving the things to the others. Okay. The similar fashion you can think of to have a certain proper application as well as use this research in practical way. And obviously, I expect that you should generate money out of whatever you work you have done it.
Well, that's not just him. Everybody needs to think through that lens.
Yeah. So congratulations to everyone. Yeah.
Thank you, sir.
Thank you.
Excellent presentation of non-linear analysis for the linear learning model. So, very good.
No, so congratulations, Dr. Suraj Bhoyar now. Okay, so we can call you Dr. Suraj now.
Thank you, sir.
But it's very heartening to see this kind of a detailed work being done and presented in such a nice and lucid fashion. I think it also triggers me to think through this whole aspect of both your supervisors and you to also start acting like a capacity building program for how do you actually go about doing all of this stuff that you've kind of put together. Because the kind of work that most of these part-time scholars are doing, right? Because they come from industry background, right? So there's no complaint against them. But the way it needs to be done, carried out in the phases, the way you have kind of presented the theoretical side of it, the analytical side of it, and the experimental side of it, right? I think the overall process of approaching the PhD or a doctoral work itself, and I know we have been talking about in the RDC, that how do you fix this whole thing where, how do you train the supervisors, because there are a lot of new supervisors who are coming on the block, right? How do you train these part-timers who want to actually do the PhD degree without really going through this whole rigmarole of getting to, whether it is simulation side, whether it is through going through the lab work. I think that rigor, if we are able to bring some aspects to that, right, I think it'll be a bigger contributor than your PhD itself, I guess, right? So while you complete your PhD today, and I congratulate you for that, but I see your bigger role both from the supervisors as well as your scholar side to create this whole culture of how do you approach this whole doctoral side of it. And we'll cover that money part of it, don't worry about it.
Thank you so much, sir. Thank you.
The best thing is, just explaining in the words what to do, you will put it in the slides and pictures. So चार लाइन ही बता दो, चार लाइन को कितना बढ़िया से उसको करना है, वो it goes beyond that. हाँ, ये you start from
No, no, and also that's the best practice. I mean, see, because to me that also comes out as a best practice from this whole work. See, if I can see the output of your work in a form of a dashboard, right? Many of those guys, and I sat through many of them, and I stopped sitting just because of the deliberate thing, that I kept on hearing a lot of these things, right? You don't tell me if you show me that this is an output, right? You just click, because there are a lot of frameworks that come up from a lot of people from either Geo or some of those guys. I mean, while they talk about the same thing of dashboardization of things in corporate, but when they come to the academia side, they keep on doing the slides part of it. So that was my complaint to every scholar that presented. So I could see that, and it was very pleasing to see the output in the form of dashboard, and you can actually play around with all of those things, right? While we could not satisfy the interpolation or the intermediate touch points, I mean, that's probably some secret. We'll have to figure that out, how do we bake in that part of it. But then I think if you give a opportunity for outsiders to play around with my results and my output, I think that itself becomes a unique platform. I don't see InfluentNet has even thought through this layer of dashboardization of the output of a PhD work. So that's a fantastic best practice that we need to probably share with a lot of people. So thank you for that one also.
Thank you, sir. Thank you so much.